Well, welcome to Lecture 6 on tensors in the General Relativity course I'm putting together here at the moment. And well, let me just get straight into it. There's a lot of different ways to look at tensors, and I suppose the tensors I'm describing here, for the most part, are just really tensors over a vector space. And I'm generally interested in this lecture just in tensors on Minkowski space, and although to be fair, sometimes we want to talk about a tensor field on Minkowski space. So let's try to unravel those things. And although to start with this first page, I believe we're really looking at tensors on a vector space. All right, so a tensor of type KL on a vector space V, we're talking about a real vector space in this context of dimension n. All right, so E1 through En is the basis for V, and theta 1 through theta n is the basis for V dual. I do sometimes specifically mean E1 through En are the Cartesian basis for Rn. So you just kind of have to watch on the context for what I mean by E1 through En. And sometimes in other courses I've used E upper I rather than theta upper I here for the dual basis. But the dual basis are defined by this rule right here. Theta I acting on Ej is delta Ij. That defines the values of theta I on the basis, and then you extend linearly, and as such you've got each theta I is a vector in the dual space, right? It's a linear mapping from the vector space to the reals. I will say, I think this lecture is going to be pretty hard to understand if you haven't had some linear algebra with me before. But anyway, here we go. So a tensor of type KL, all right, is a mapping, a multilinear mapping from K copies of the dual space and L copies of the vector space to the reals again. Well, I would say more specifically, this is a real valued tensor. Of course, you could take tensors that take their values in something else, like a matrix or whatever, but by default, we're talking about real valued tensors. We're also going to identify the double dual by the rule V acts on alpha according to alpha acting on V. That allows us to think of vectors as active objects which eat dual vectors. So-called canonical isomorphism of V and its double dual. It's okay for finite dimensions, I suppose. Anyway, with that, we can express T as a sum of tensors of. So here I'm using tensor as a different. Here I'm using tensor operatively as a method of putting together these maps, E I sub 1 through E I sub k, and theta j sub 1 and through theta j sub k. So you can take the tensor product of maps, and so you take these and you pick appropriate numbers out here, right? You sum over those things and you can form the tensor T. Now, here's how that actually works out. Now, I haven't actually taken the time to carefully define the tensor product of those maps, but it's essentially equivalent to the formula I write right here, and here it is. So if we have this tensor acting on these covectors and these vectors, you feed it to T, and so I'm claiming that if you feed this K plus L tuple of covectors and vectors into this contraption right here, what pops out is just EI1 of alpha 1 EIK of alpha k, right? And then theta j1 of v1 theta j sub l of v sub l, all right? So if I took the time to define the tensor product of maps, you could prove that the tensor product of maps was itself, in fact, a multilinear mapping of the appropriate type, and hence a tensor. And then you can prove that the sum of such things is again such a thing. And then you can prove, in fact, that this provides a basis for all such type KL tensors. I haven't quite done all that, but I've given you some of the formulas you need to do that. Anyway, as I will explain in more detail in one of the future pages here on this lecture, when you take EI1 and act on alpha 1, you just get the I1 component of alpha 1, and this picks off the IK component of alpha k, and likewise we're picking out the it's pretty neat, like the basis or the dual basis acting on forms or vectors, it just ends up picking off the components, the corresponding components of said dual vectors or vectors, just like that. So let's see here. So this, and then you can also show that, in fact, the way to get these numbers here is to evaluate on the dual basis and the basis as appropriately matching the indices. And so actually this little calculation here shows you that that's the case. So like if you believe what I wrote before, if I plug these into T, I get this formula, right? And then these are Kronecker deltas as given here. And so what that does is it squashes the sum and shows you that the I1 IK component, J1 JL component, like so, is in fact given by evaluating T on the corresponding K tuple of dual vectors and L tuple of vectors as appropriate. So, I mean, if you want me to put the cart back in order, you can do something like define T sub, define this by that, and then you can prove that if we define this by that, then this formula, this formula up here becomes an identity. So anyway, I should mention, typically, our larger application for tensors as we go on in this course is that we want to talk about the vector space being the tangent space at P to a curved space, which we'll think of space-time, curved space-time, and the dual space will be the cotangent space to curved space-time, right? But in this lecture, for the most part, we're just thinking of M itself also as Minkowski space, so it's kind of silly in a sense, but we can think about vectors and covectors at each point in Minkowski space, right? So attaching a vector at each point in Minkowski space gives you a vector field on Minkowski space. Attaching a covector at each point in Minkowski space would give you a one form on Minkowski space, and so forth. So we can talk about tensors at a point or tensor fields, just like we could talk about vectors or vector fields in calculus, you may remember. So here's some examples, just to get us used to the notation here a bit more. So if we have a vector v, all right, and a dual vector alpha, then we can expand v as sum over the basis ei and alpha as a sum over the basis dual basis theta j, and when we calculate alpha on v, we've got this acting on that, but by linearity of the theta j's I can pull the I'll get it right here eventually. So how to explain this? So I can pull the vi's out, right? Because we're assuming theta j is linear. So I can pull those numbers out, and then I have theta j acting on ei, but by definition of the dual basis, that's Kronecker delta ji. Now, maybe I should be writing j upper or I lower here, whatever. In any event, we get vi alpha I. And likewise, when we take v acting on alpha, right, we go through the calculation here. Again, using linearity. Well, okay, fine. To be fussy here, Alright, fine. Alright, bothering me. So how did I define, this is very silly, but EI, right, acting on theta j, what does that mean? Well, this is a vector acting on a covector, right? So by definition, we said that was, and this is, you know, the identification of the dual with the double, I mean, the vector space with the double dual that I was talking about a second ago here. This is theta j acting on EI. And that, by definition, is Kronecker delta ij. So that's what's missing in that line right there, is that detail. So that's why I know that EI acting on theta j is delta ij, because this is understood to be theta j acting on EI because of the canonical isomorphism between the vector space and its double dual. And so there's that. So anyway, whichever way you slice it, if you have a covector acting on a vector, or if you have a vector acting on the covector, either way you get the contraction, the sum over the components of the vector with the dual vector, either way. And this calculation is good for any vector space and its dual. All right, as long as we're talking about a basis and a dual basis, like this is not special to Minkowski space or anything like that. Well, it's either a fire or something. I don't know if you guys can hear that or not, but something exciting is happening here. Well, shall I let it pass? All right, so we've got a tensor of type 2, 2. We're going from V dual cross V dual cross V to the reals. And I want to just see what does the formula look like if we feed it alpha beta covectors and V and W vectors. Like, what's the formula for T acting on this, you know, pair of covectors and pair of vectors? Well, so you feed. So here's the, you know, the formula for Tijkl, contract over I, contract over J, sum over I, sum over J, sum over K, sum over L, right? It acts on all this, and what happens is you get EI on alpha, you get EJ on beta, you get theta K on V, you get theta L on W, all right? That's the definition of this tensor product of maps. When it acts on something, that's how it acts. It just feeds this to that one, this to that one, the third one to the third one, the fourth one to the fourth one. And then you can prove a lemma that when we have EI acting on alpha, you get alpha I. Likewise, EJ on beta gives you beta J, and, you know, again, theta upper K on V gives you VK, theta upper L on W gives you WL. And so with this lemma in mind, when we calculate the tensor acting on these objects, we just get the tensor components summed over the components of the objects that you're acting on. So it's very cool. Uh-oh. Uno momento. 30 minutes, maybe? Sorry, guys. All right, moving on here. I better silence this. So we have a lemma. Here's the lemma I just used. Theta I acting on V gives you V upper I, and E alpha acting on alpha, E sub I acting on alpha gives you alpha sub I. So here's the calculation. We let V be, you know, where was I? Let me scooch this up a bit here. So we have V summed over the basis EJ, and so when we let theta I act on V, we have this. Linearity allows me to pull the sum over Vj out, and then by definition we had delta ij for that, which gives us Vi. Yay! Likewise, if we look at alpha on EI is this, which again is alpha j, and then that gives us Kronecker delta ji, which is alpha I. So there you go. I mean, not complicated, but there it is. Another example. If we have the metric like so, then we have, we can expand it in terms of tensor product of the dual basis like so. And when I do that, well, it doesn't have to be a metric. This is just a bilinear form, rather. Right, so I guess type 0, 2, I think, in our current language tensor. So VW, and so we can expand G like this, and when you feed V and W into the tensor product of the thetas, you get VI, WJ like that. And there's that. Now, in Carroll, I should mention, he's got hats and stuff. He's putting hats over things that are not numbers, whereas things without hats are numbers. I'm not going to start doing that because I can't do it. So you'll just have to depend on context whether I'm talking about an object or a number. And even the numbers aren't numbers. Sometimes they're functions, right? So let's see here. Let's talk about raising and lowering indices in Minkowski space. Generally, the metric G mu nu has inverse G upper mu nu, and they're not equal. But for the Minkowski metric, it is actually equal to its inverse component-wise. But we try to distinguish this and that in formulas, because later we want to distinguish between upper and down, upper and lower metric, because they are generally different. Anyway, here it is, how to lower indices. So if we want to, if we have, rather raise an indice, if I want to raise the mu index here on alpha, we define it to be alpha upper mu, which is defined to be eta, we denote it by alpha upper mu. It's defined to be eta mu nu, alpha lower nu, like that. To lower the index on V upper mu, we denote it by V lower mu. It's defined to be eta mu nu V nu. So notice the contraction over nu there. And if you want to raise a pair of indices, you just use two etas like that. So here's the explicit details, like breakdown here, what that means. So for a vector, if these are the components of the vector with the index up, so these are the so-called contravariant components. The so-called covariant components are down here, and they're equal in the Minkowski metric for the last three, but they're minus each other in the first two. Now that's relative to our convention. There's another metric sometimes people use, which is 1, minus 1, minus 1, minus 1, and there the time components would match up, but the spatial components would be minus each other. All right. But anyway, let me stick to our conventions. Likewise, when we raise the index on a covector, we get the same, the same indices here, same components for the spatial part, but the time component differs by a sign, right? In other words, you could say this. You could say alpha sub I equals to alpha sub I, but alpha sub 0 is minus alpha sub 0, upper 0 rather. And that's kind of it in a nutshell. All right. Now it's more interesting, of course, for the rank 2 tensor down here. I should be careful. The term rank in mathematics tends to have a more nuanced meaning. In physics, when we talk about rank, we're just talking about like the type usually. So like type 0,2 makes it rank 2, or type 2,0 makes it rank 2, or type 1,1 makes it rank 2. So rank is just the number of indices in physics typically, but in mathematics, rank is something more like the dimension of a particular subspace as it's related to the object. Like usually, like the rank of a matrix is the dimension of its column space. All right. Anyway, back on track here. So if we raise the index for a tensor of this type with two lower indices, then it ends up being that if we have 1, 0 and 1 spatial, then we get minus the spatial is equal to spatial up down, doesn't do anything to spatial. because there's two minuses for time, we just get equality there, and again for space time, it's minus again. So here's a picture. Oh man, dummy. I really need to have, this should be mu up here obviously, otherwise it's really dumb. Sorry about that, let me fix that. Alright, well I haven't scanned this yet, so no harm, no foul. Oh, uh-oh, the wind. So that's how you raise and lower indices. We'll see the necessity of that and why it matters, especially to constructing equations in physics. Super important. The main thing is actually what's right here, which is that if we have raising and lowering indices, it's a way to construct what are called scalars. Alright, so just to reiterate here, vectors transform contravariantly, covectors transform covariantly. So if we change coordinates, this is how a vector transforms. If we change coordinates for a dual vector, this is how they transform. If we change coordinates for a tensor, we get one Lorentz matrix for each index and one inverse Lorentz matrix for each lower index. So the lower indices transformed by the inverse matrix, the upper indices transformed by the matrix. Here I mean to say that the matrix is the one which transforms the coordinates, whereas the inverse is the one which, well, it goes the other way. And they're inverses in the usual sense of linear algebra, like the matrix times its inverse is the identity matrix, and vice versa. If we're in the context of Minkowski space, we also know that the Lorentz transformations satisfy this eta lambda transpose eta lambda relation, right? So here's just a quick calculation, because I'm going to run out of time here if I'm not careful. The invariance, let me see how much time I have left. All right. So if we want to calculate the invariance of this, what I want to show you is that if we contract a vector with its lowered, so if we take a vector, we lower its index, right? Then sum over that. This result is independent of coordinates, and it's an invariant, also known as a scalar. All right. So let's see how that goes. So I take my v mu prime, I leave it alone. I raise the index on v. I'll get it right here. V mu prime is fine. V lower mu prime is the lowered index, right? So that was defined to be eta mu prime alpha prime contracted over v upper alpha prime. And then I put in the coordinate change rule, the contravariant coordinate change rule for both of the v's right here. Then I pull my lambdas out, I look at it, tilt my head and squint, and realize, wait a minute, this, by definition of lambda, is exactly eta nu beta, and so lo and behold, that is, I can lower the index here, or I like to lower the index on this one. So v nu, I can make that into a sub beta by this one here. Don't worry about the order of nu and beta, since nu is symmetric. V nu beta is v beta nu. So like, it doesn't matter which order they're in here for that. The point is that these two can become that, and then we've got sum over beta, so, and of course you can also write it like that. These are just numbers that commute. My point is that this quantity, when we contract a vector over its index lowered version, this gives us a scalar, all right? And in fact, I suppose I would be negligent not to mention that this is exactly what you get from, pretty sure this is what we just would, I mean, this is the vector, right, transpose eta times the vector again anyway. This is exactly that scalar. See, because you work this out, it's minus v0, v0, upper 0, plus v1, v1, plus v2, v2, plus v3, v3, plus, yeah, well, there. So that is the significance of that scalar. It's the Minkowski product of the vector with itself. All right, coordinate change. So just to reiterate again, we have the Lorentz transformation, and then we have its inverse. And if you put these two together, you can derive that, in fact, the matrix for the transformation and the matrix for the inverse transformation, they do have to be inverse matrices, like I claimed a second ago. It's true. So this is the relation. Notice that the order of the primes tells you it's a giveaway, right? So like the forward transformation has the prime second, the inverse transformation has the prime first, and that's how you can tell which is which in this nomenclature we're using. And I said geometric. What's a geometric object? A geometric object is an object which is defined independent of coordinate systems, really. So sometimes something appears to have a coordinate dependence like this, like a point, P, right? It's e mu, but what happens if you describe it with a different coordinate system, like mu prime? Well, it's just the same, right? So like, that if you were just to refer to P by P upper mu, it appears to be coordinate dependent, but it's not really, because the proper description of P involves both the coordinates of it as well as the basis for the coordinates which you're using, and those transform inversely. See, the basis transforms inverse to the coordinates, and as such, if you used a different coordinate system, you'd still have the same P. So the point or event in space-time exists independent of the particular coordinate systems used to describe P. Similarly, if you describe a vector as a sum over the basis, well, it's a vector field on space-time, you can write it either as this or as that, and that's consistent because if you transform these, the v upper mu prime and the e lower mu prime transform inversely, and as such this is a consistent formalism. Likewise for one forms, since the components of the one form and the one form basis transform inversely, see that? They transform inversely. When you change coordinate systems, you just get a pair of a matrix and inverse matrix, all right? Same thing happened up here. The components transform inversely to the basis. And by the way, this is nothing special to special relativity. This is a general facet of linear algebra. When we study coordinate change, the coordinate change of the components of a vector transform inverse to the basis of the vector. All right. Let's talk about partial derivatives of a tensor field. So, if we have the following coordinate change rule, right? X mu prime is lambda mu prime nu x nu, all right? Then if you differentiate that thing, right, with respect to alpha, x alpha, then by the product rule in principle I'd have this and that. But in practice, since this is just a constant matrix for a Lorentz matrix, right, this has no dependence on coordinates, that's 0. And of course by just usual partial differentiation, that's Kronecker delta alpha nu. And so lo and behold, you got partial x mu prime, partial x alpha is lambda mu prime alpha. So we find that the partial derivative of x mu prime with x alpha is in fact the Lorentz transformation at play between the prime system and the unprimed system, all right? That's pretty neat, because in curved space, if we study general coordinate transformations of the form, let's say x mu prime equal to, lambda tilde, I put a tilde on it just to try to make a logical distinction here, lambda tilde mu prime x nu, right? If you had something of that form on curved space, if you could write the transformation that way, then when you took the derivative, you would get a piece where you're picking up the coordinate dependence of the transformation, and so it wouldn't just be what we found before, and this would actually end up spoiling what I'm about to show you, all right? And that's this theorem, which is if you have a type PQ tensor, like so with the, here's the components for the tensor, all right? And then if you take the partial derivative of those components, well, in fact, those are the components of a related type P, Q plus 1 tensor. All right, and here's the proof. So what I'm doing here is I'm showing you that the coordinate change property of the this tensor is what it should be. So to show that it's a tensor, looking at the level of components, we have to show that the components transform correctly according to the type of index that it has. So, first of all, I take this type PQ tensor and I put in the appropriate copies of the Lorentz transformation and its inverse, like so. And then I notice that these are all constant, so I can pull them outside the differentiation, right? Then I use the chain rule. The chain rule says that differentiation with respect to x lambda prime is equal to differentiation of x lambda with respect to x lambda prime summed over the x lambda, like that, right? And then, well, we also know that by the previous discussion on this page, partial lambda prime is nothing more than the Lorentz transformation, lambda prime, like so. And as such, I have exactly what I need to satisfy the necessary transformation law on this symbol to be a type P, Q plus 1 tensor. So here I'm going back to, you know, where we started, ways back here. Well, I guess I didn't. Oh man, did I never actually say it? Ah, curses. Well, I never came out and told you the transformation law for a tensor, did I? My bad. Well, I guess this is kind of a rough way to learn it, but so this was the transformation law for a contravariant index, for a covariant index, and basically when you have more indices, you need this pattern for each one of the index. Oh, here it is, right here. I said it, but I forgot it. So this is the general transformation law for a tensor. You have to have this in order for a tensor to be geometric, because these get contracted over, you know, basis and dual basis vectors, and because they transform as they do, it must transform as you see here. Otherwise, you would get a coordinate dependence. But anyway, so that's the general tensor transformation law right here. And what I was just showing you is that the partial derivative, in fact, transforms in that pattern like it's supposed to, so therefore it's a tensor. This is how physicists prove things are tensors, by studying their transformation laws. Alright? Moving along here. Some other things we can talk about, some tensor arithmetic. So, given a particular tensor, in this case a type 3-2 tensor, we can define several new tensors by contraction. So contraction is when you sum over an index pair. So like here I'm summing alpha, but I left the beta and the gamma and the nu alone. And this time I'm summing over alpha, but this time I put alpha summed over the second lower index there, right? This one I'm summing over beta on the first lower index, and now I'm summing over this beta on the second lower. So like basically the second upper index to the first lower index, the second upper index to the second lower index, and finally here I'm summing third upper index to first lower index, third upper index to second. I mean, these are all different possible contractions you could make of a type 3-2 tensor. You got all kinds of choices. Or you could contract two pairs, right? You could contract two pairs. You could contract like this with that and that with that, leave the gamma. Or you could contract, you know, the first upper index with the last lower index, and the second upper index with the first lower index. And, you know, all these other possibilities. So here I've left the index gamma as free. Here I've left the index alpha as free. Here I've left the index beta as free. My point to you in all of these is that there are tons of ways to construct new tensors from old. And when I say that these are tensors, I'm not just saying that that's an allowed formula. I'm saying that the coordinate change properties of all these expressions I've written down are exactly the kind I write over here, which means that if you were to write down, like, you know, these with like a beta prime, so if you had, like, you know, you could call this thing, you could define this thing to be, you know, S, let's see here, I said beta, right? S upper beta equals this, right? then if you were to study S beta prime, you could show that that's equal to lambda beta prime beta S beta. It would transform as a type 1,0 tensor, right? And similar comments apply up here. I haven't proved that, I'm just claiming it's true, you know? Although I think I've given you enough formulas you could prove it. That sounds like a homework problem. Okay, so just to explain here what's going on, these may all be distinct if T has no symmetries, but when T is symmetric or anti-symmetric, in particular index pairs up here, it could be that some of these different contractions in fact are the same animal. All right. A couple more comments here. If you want to raise the indices on this gadget, so like raise these last two indices, you could talk about T alpha beta gamma sigma rho, and the way to do that would be to put a eta mu sigma and an eta nu rho and contract those over the mu and the nu like so. That would be how to raise the last two indices on this tensor. If you wanted to lower the first three indices on this tensor to sigma rho delta, and I'm leaving the mu and nu alone, well then you need three etas, one for each index like so, and you contract over them as such. Fun fact, if you want to, you could kind of calculate a scalar from the tensor by just contracting all of the index ups with all the index down like that. If you do that, since you have a matching number of contravariant and covariant indices, it will be the case that this forms a scalar. And here is the scalar explicitly in terms of the original tensor and the appropriate sums over eta. I mean, there you go. These are the kind of games you can play to create coordinate invariant objects in special relativity. You can contract indices and raise and lower them to create formulas which are independent of coordinate system. That's important because Einstein told us that the laws of physics should be independent of coordinates. So if you're looking for a law of physics, then you're looking for scalars in part. More fun with tensors. Woohoo! So this is symmetrization in mu and nu. Hold the nu. So mu rho. Symmetrization in mu rho. Hold the nu. There we go. So nu stays put, and the mu and the rho flippy flop like that. If you were symmetrizing in nu and rho, the mu would stay put, and you do nu rho rho nu, the half out front. If you were anti-symmetrizing in mu and rho, the nu stays put, and you put a minus. You get the idea. Here's what it looks like for three indices. Here's what it looks like for the symmetrization of three indices, the anti-symmetrization of three indices. Of course, you could add another letter over here, and it would just ride along, you know. And you can even think about interrupting this symmetrization or anti-symmetrization of three indices with like a, kind of like we did up here, like insert a mu, nu. But you know what? Let's talk about it when we need to use it. One thing that's important, and I found surprising when I was first studying this stuff, is that you can write any pair of indices as a sum of its symmetrization and anti-symmetrization, but this is only for two indices, not for three or more. Like if you look at this up here, if you add these two expressions, you don't just get back T alpha beta gamma. And I mean, it's just not that. So the way these interact are much more complicated. To break down three indices, you need to study like how you break a tensor into its pieces. That's representation theory. It's more complicated. The combinatorics are more nuanced than just adding two things. But for two things, you can get away with it. So we have this is equal to that, but this is not equal to that. It doesn't matter if you've got more indices riding along. Same comment holds. Finally, an example to finish this somewhat hurried lecture. My apologies. If a mu nu is anti-symmetric, we can quote-unquote simplify the contraction below. So if I'm summing T mu nu over a mu nu, T mu nu, remember, I can write as a sum of the symmetric and the anti-symmetric piece. But remember what we learned a couple lectures ago? If we have symmetric summed over anti-symmetric, it's 0. So this piece drops out, and you're just left with that, which is equal to this, which I am claiming is simplified. I don't know. my point is to you that this is a calculation we can do. You know, if we knew more details about the t mu nu, this might actually flesh out to be a simplification. So, you know, again, sums over symmetric and anti-symmetric vanishing is often a important thing to notice for a particular problem. Well, okay, so we've just dipped our foot in the pond here, so to speak, with the tensor calculation. I hope this gives you a sense of it. These are things we'll be doing. We like to contract indices. We like to raise and lower indices. We like to think about coordinate change of tensors. You know, so this notation of the prime and unprime notation for the matrix and its inverse, I know that's new for math majors for sure. So you got to watch out for that. It'll sneak up on you if you're not watching out for it. Like in my current state of being, I have to look it up to make sure that I'm not butchering the notation. Hopefully I haven't butchered it here. And I think next lecture past this, we're going to take a look at how to write Maxwell's equations. Using tensor notation. And that's one of my favorite topics, actually. And it kind of involves most of this. So anyway, I think that's it for now. So thanks, guys.